Hello and welcome to our 21st session. In today's session we'll be continuing with the material in Chapter 12, which is the p-n junction diode in non-equilibrium. Last time we looked at reverse bias. Today's session we're going to be looking at forward bias, and forward bias involves the minority carrier diffusion equation, and we'll be looking at different lengths in the quasi-neutral regions, specifically long, short, and intermediate ranges. The long is pretty straightforward. The short is the easiest. The intermediate is quite a bit more difficult. And then we'll be looking finally at the charge control model. And probably won't finish, but we'll wrap it up next time. And next time also we'll be looking at a really interesting structure called the pin diode. It's P intrinsic N type silicon, and that will be our first three-terminal device, which would be a nice segue into the bipolar junction transistor, which is also a three-terminal device. Before we begin, I'd like to share with you a finale of Franz Joseph Haydn's Hockermeissen, the kettle drum mass in time of war, and we'll be listening to the finale, Dana Nobis Passion, Lord grant us peace, and we'll see you in about 3.5 minutes. Okay, so these are the topics we'll be covering today. All of our work is going to be in forward bias. Forward bias in a p-n junction requires that we use the minority carrier diffusion equation, and we'll be looking at the minority carrier diffusion equation under a number of different conditions, different recombination times, and different quasi-neutral lengths. And then we'll be looking at a variation to find the the current in a p-n junction called the charge control model, and we'll be looking at that under two conditions, along and a short base p-n junction diode. And finally, we'll be putting this all together with an arbitrary conditions, arbitrary widths, and arbitrary recombination times. And that's going to be rather challenging, which is why we started with the Haydn Mass and Time of War, the Dona Nobis Pacem, Lord grant us peace, and hopefully we'll be granted some peace by the end of the day. Okay, so let's take a look first at the structure of the configuration. This is a p-n junction, P on the left and on the right. P is more highly doped than N because the depletion width on the P side is lower. There is a barrier that goes from both sides. There is an electric field, an internal electric field, which goes from right to left, and that is in the negative direction. We know that this is in forward bias because there is an external electric field which is opposed to the internal electric field. The external electric field goes from left to right. That's why the left side is positive with respect to the right side. So because there is an internal electric field, the barrier has been reduced, the depletion region has been reduced, and majority carrier electrons are able to surmount the barrier and become minority carrier electrons in the P region. And the same thing happens in the P region, that majority carrier holes are able to surmount the barrier and become minority holes in the N region. The barrier is a two-way barrier, so if we lower it for electrons, we lower it the same amount for holes. The barrier for p-n junctions is generally much larger than for Schottky's, generally running somewhere in the 0.6 to 1 electron volt range. So that's going to require a fair amount of forward bias to overcome that. So forward biases are generally in the 0.5 to 0.7 electron, or not electron, 0.5 to 0.7 volts for an external voltage VA. Okay, so we said that we're going to be using the minority carrier diffusion equation, and here it sits in all its glory. There are four terms. The first term, or I should say the term on the left, is going to be 0 because we are generally going to be in steady state and we're not going to apply light. So this term is 0 and this term is 0. I should mention, perhaps parenthetically, that these two terms go together. Whenever we have light, we're generally not going to have steady state because we're going to be turning the light on and off. But in the p-n junction, these are the two terms that we'll be concentrating on. And we see that right here. The current in the p-n junction, let's say on the N side, is equal to minus the excess electrons in the P region divided by the recombination time for those electrons in the P region. Okay, so this doesn't look too bad, but we're actually going to make it a little bit easier because this is not an easy subject. And we're going to require that tau sub n go to infinity. That can be done by making the p-n junction, the material, very pure, and or making the quasi-neutral regions quite long, so there's not enough time for the excess electrons in the P region to recombine. So then we have equation 12.20. We still have electrons which are going from high concentration at the border, where they just are able to surmount the boundary and haven't yet traveled very far into the P region, so they have a high concentration, and in the rest of the P region there's a low concentration, so electron motion is from right to left, which implies that the current is from left to right. Electron flow is always in opposition to current, and that's in the P silicon. Okay, so this equation is very nice. It really doesn't tell us how to solve for the diffusion current because there is no delta N in this bad boy. So we need also the diffusion current itself, and here it sits. This is the diffusion current as a function of the excess number of electrons, which of course is a function self of position. And you can read this and find out why this is a positive current, because delta X is negative, I should say dx is negative, so this is a positive current. Electrons are moving from right to left. And let's just recall the notation. This is the second time around here. We're going to be using terms like this. The first term, the big term, will be the charge type. So this refers to electrons, and the first subscript refers to where are those charges. Well, this is electrons in P. So this refers to minority electrons that happen to find themselves in P-type silicon. 0 refers to the fact that it is in equilibrium. Without the 0, it is not in equilibrium. So, for example, NP0 in a material which is doped 10 to the 16th would be 10 to the 4th. The number of electrons in P-type material of 10 to the 16th in equilibrium would be 10 to the 4th. Without the 0, however, it can be much higher than 10 to the 4th. And that is the case here, where we have minority holes in N-type material without the 0. So that's a big deal. The excess is just equal to the non-equilibrium minus the equilibrium. That's the amount of electrons, for example, which are in excess of equilibrium. This term will generally be quite small. This term can be relatively large. Could be 10 to the 5th, 10 to the 6th even, quite large. And this would be 10 squared, 10 cubed, something like that. Okay, so if we, oh boy, all the way back here. If we put this equation into this equation, we get, for the diffusion current, there it is, for the number of excess carriers. It's a second derivative, so this is a second order differential equation. This is when we have a finite recombination time. Well, if you look at this equation, there is only one function that can satisfy it, and that is the exponential. An exponential is the only function, when we take its derivative, we get back an exponential. And we take its derivative again, and we get back a exponential. So we can write the solution by inspection as a sum of two exponentials where x is in the quasi-neutral region for P less than the depletion region width. So this is the depletion region with WP, and we're in this region right here. So that is the solution, and we're going to be coming back to that a little bit later on. And just one other thing before we leave this. We notice that the term here must be a distance, and the reason is because the power in the exponential must be unitless. So if I have centimeters on top, I must have centimeters on the bottom. And we will show that the thing called diffusion length is equal to the square root of the diffusion constant multiplied by the recombination time. Now, let's take a look at another case where the recombination time is infinite. So we have the second derivative equal to 0. If the second derivative is equal to 0, the first derivative is constant, and the second derivative of the integral of the first, I should say, yeah. Let me go back and say that again. If the second derivative is 0, the first derivative is constant, and the function itself, delta n of x, is linear. And that's what we see here. So if we have an infinite tau, the form of delta n is linear. If we have a finite tau, the form of delta n is exponential. Now, that shouldn't be too surprising because we can expand the exponential term in a Taylor series as a constant plus a linear term. So the fact that for large LNs, or for small x's, or for large recombination times, it's all the same, we get a linear variation here. Equation 1224 should not be too surprising. Okay, so now let's take a look at this a little bit more in detail, a little bit more quantitatively, a little bit more mathematics. Repeat this basic structure here, and we're talking about n type carriers, electrons in the p-type silicon, and we want to find out what the delta n is as a function of x, given that we know the boundary conditions, or at least we'll find out the boundary conditions, we know the delta n, or we're going to find the delta n at the edge of the depletion region right here, where x double prime is equal to 0, and we're going to find the delta n at the end of the journey. Well, we can say the delta n at the end of the journey must be 0, and that's a condition. Once these excess minority carriers get to this point right here, they basically become 0, because we can have no excess minority carriers, or we can have no excess charges in the contact. Contact is a field-free region, so we're going to require that delta n goes to 0 at the end of the journey, which is the contact right here. Okay, now we've already derived this equation for the number of holes and electrons if we have forward bias of VA. And just to use our notation here, PP, which is, of course, equilibrium at x equals x double prime equals 0, that's NA. That would be, for example, if NA is 10 to the 16th, P sub P would be 10 to the 16th. N sub P, again at equilibrium, is just 10 to the 20th, or 10 to the 10th, sorry, divided by NA. So if NA is 10 to the 16th, then NP would be 10 to the minus 6th. So that's quite a low value. However, the VA jumps it up. And let's just do an example. If we have VA is 0.6 volts and the p-side doping is 10 to the 16th, then we get 10 to the minus 6 for the first term and 10 to the 10th for the second term. So we get about 10,000 excess. So the excess electrons at the depletion region edge in the P region is about 10,000. Okay, this points out that the total current should be dominated by the side which has the lower doping. For example, if I had N sub A is equal to 10 to the 15th, this would be 100,000, not 10,000. And for example, if I go back here, if I have 10 to the 15th over here and 10 to the 16th over here, I'm going to have a higher value of excess holes than I have of excess electrons. So that the total current will be dominated in the side which has the lower doping. And we'll see that a little bit later on. Okay, so this, let me just make this a little bit clearer here. There we go. Okay, so we have the excess electron concentration at the edge of the depletion region. We have the non-equilibrium, and then we have the equilibrium. This is the excess, the non-equilibrium minus the equilibrium. And here it's shown explicitly, and we just combine the terms, and equation 1230 is our basic equation. Many times, in fact most times, we will just eliminate this and we'll just use the first term because this term is very small compared to this term. And we can do exactly the same thing on the n side. We have the equilibrium concentration on the n side. Here it's x prime, not x double prime, and that of course would be equal to the donor doping density. The excess holes on the n side will be equal to the non-equilibrium holes on the n side minus the equilibrium holes on the n side. And comparing equation 1232 to 1230 here, we find that the only difference are the dopings, and that's it. That is the only difference. Okay. So the excess numbers, the absolute terms, will depend inversely on the doping. Low doping, high excess. High doping, low excess. And that's a big deal, but in both cases there is a boost, for want of a better term, which is exponentially dependent on the applied voltage. So for 0.6 volts, it is 10 to the 10th. By the way, if it was okay, that's okay. For 0.6 volts, it's about 10 to the 10th, and we saw that in our last example. Okay, so let's carry this forward a little bit. Actually, this time we're going to work on the n side. So these will be minority holes in the n side. So we know what the solution is for the minority holes on the n side for x greater than x prime. So this is all in this region here. It is a linear function of x. There are two constants. There are two boundary conditions. At 0, which is right here, that's the edge of the depletion region. This region here would be the depletion region on the n side. So at the edge of the depletion region, where x prime equals 0, we know that this is the excess number of carriers, and at the contact, which we call XC1, we have 0 excess carriers. So that is an important boundary condition, and because of that, we just plug those boundary conditions into the expression, and we find that A1 is equal to, or given by equation 1236, and A2 is given by equation 1237. That basically just uses these two conditions in equation 1233, and now we have the complete diffusion current in the N region. Notice that we have a P here, so this is kind of confusing, but what it says is it's a diffusion constant for holes in the N region. And so we have an expression now for delta P, which is somewhere, it's right here with our boundaries, and so we just differentiate it, and that gives us the diffusion current. This is the general expression for the diffusion current. We have an expression for delta P, and we just plug it in and use the basic result here. And notice, and this is important, that the diffusion current is constant. There's no X here, and that's nice. That's what we like, and that is something that is quite desirable. We can do the same thing on the N side, and notice the only difference is there are different quasi-neutral regions. One is XC1, the other is XC2, and the dopings are different. But this dominant term right here is the same, and that's the important thing. And then we just add them together, and it is a constant. The total diffusion current is equal to the diffusion current of holes on the N side plus the diffusion current of electrons on the P side, and here it says, and they are positive, and we don't subtract them. They're in the same direction. Electrons moving from right to left, which is current moving from left to right. Holes moving from left to right, which is, of course, again, is positive current. So there is a plus sign in equation 12.40. So just to summarize, this is the good stuff. This is what we want. This is what we're aiming for, and generally we get it in the base of a bipolar junction transistor, a constant current. Now we tackle the case where the diffusion, the recombination time is not infinite. So that's a little bit more involved because we have exponentials rather than a linear function. But again, if LP and LN are quite large, then the exponential will basically turn into a linear function. But we're going to assume here that that is not the case. In fact, the first case we're going to be assuming is that the quasi-neutral region is much greater than the diffusion lengths. Okay, but before we start on this next case, which will take us into the charge control model and the general case, which is going to be a fair amount of work, I need to correct something which I did. This was really an idiotic mistake that I made. Not the first time I make idiotic mistakes, but if you were looking at this and you did not have the urge to throw something at the computer screen, that's not good, because this was really a bad error. So I want to go back here a couple of pages, and right here, this is a disaster. And it's a disaster because it looks innocent, but it's a disaster because the units don't match on the left and the right side. The units on the left side are concentration, which is numbers per cubic centimeter. The units on the right side are, well, they're unitless. Concentration divided by concentration. And, of course, the units of anything exponential are unitless. So I've got units here of centimeter to the minus 3, and I've got unitless, no units on the right side. Where's the problem? I think you can perhaps say realize it's right here. This should not be Ni, this should be Ni squared. So instead of 10 to the 10th, this should be 10 to the 20th. And instead of 10 to the minus 6, this should be 10 to the plus 4. And instead of 10 to the plus 4, this should be 10 to the 14th. So let me correct those very quickly and get the right answer. Okay, so now we can go on with a clear conscience. The excess minority carrier concentration, the number of electrons in the P region at the edge of the depletion region, I should say the number of electrons in the quasi-neutral region at the edge of the depletion region on the P side is equal to 10 to the 14th and not 10 to the 4th, and the equilibrium number is 10 to the 4th, so we're 10 orders of magnitude greater than we were before. And I need one. This should be one more correction. I got to take that minus sign away. Okay, so now we have a completely clear conscience, and everything is as it should be. So we can go back now and go back to the case in which, right here, in which the quasi-neutral region is very much greater than the diffusion length. In that case, you can consider this as if the contact is out essentially at infinity. So what happens here is that all of the electrons in the p region recombined, all the holes in the n region recombined. So the current that we get at the end at the contact is essentially zero because they've all recombined. A very, very bad situation. That is a really, well, it's a useless, completely useless device as compared to the device up here where we have a linear variation. This is the best because here when we differentiate this with respect to x, we get a constant current all through the quasi-depletion regions. Here we get current which exponentially decreases until it essentially goes to zero. Okay, now let's take a look at the charge control model. And before we do that, I'm not sure this is a particularly useful equation here, but the basic equation for diffusion current in the depletion region at the edges of the, I should say this is the basic equation for diffusion current in the quasi-neutral regions at the depletion region edge is given by here. Notice there's no x here. What happens in this case is that the instead of having a W here, I've got the diffusion lengths, and this is a pretty good giveaway that I'm going to be in real trouble and I'm not going to get any current at all at the contacts. And of course current is equal to just the cross-sectional area multiplied by the current density. And that's exactly what happens here. The current is exponentially decreasing, and that's not shown here, but if I put in the x's here, it would be an exponential decrease as I move away. It's very high at the depletion region edge. That's this. It's great. I'm looking terrific. I got lots of current. But not so good. It recombines, and eventually when it gets to a certain distance, the slope becomes zero for the excess minority carrier concentrations, and therefore the current goes to zero because the current is the slope with respect to the derivative with respect to x. Okay. So the charge control model asks a relatively straightforward question. What's the total charge here? Well, the total charge is just going to be equal to Q, charge of an electron or hole, multiplied by delta Pn, multiplied by Lp. And this is rather an interesting quirk, if you will, or advantage, or a wonderful characteristic of exponentials. If I take a look at the Lp, this characteristic length, which is just 1 over e to whatever the function is, it looks like this is the area under this curve is the same as the area of a square of width LP, not a square, a rectangle of width LP and height delta Pn. So if I would have made this into a square by essentially squaring it off, or actually I should say a rectangle, by making it into a rectangle here, I would just find the area of the rectangle is delta Pn times Lp, and that is exactly what I have if I know LP and if I know that the curve is an exponential. So I use the definition of current. It is charge per unit time. I know the charge, and I just put that in. And the time that it takes for that charge to dissipate is the tau p, the recombination time. And I have an expression for delta n, for delta Pn at the depletion region. That is the depletion region edge, which is this point right here when x is equal to 0. That is, and this time I remembered to make it Ni squared. That is the equilibrium, and this is the so-called boost, and I generally will suppress the -1. Here I don't, doesn't matter. But this is now the current, and that is exactly the same expression that we got for the current at the depletion region edge when we use the more complicated formulation. And here I say that the diffusion length squared is equal to the diffusion constant multiplied by the recombination time. And we can see that simply by using units. So d over mu is kt over q. I know the units for the mobility, and therefore the units for d are centimeters squared per second. Actually, I don't know that because of that, but the units for the diffusion constant are centimeters squared per second. We've seen that a number of times before. So this equation makes sense, and I can rewrite that as L over tau is dP over L, just separating out the L's, and I get the final equation that this is the desired result using the charge control model, and it's done in a much more pleasant and elegant fashion than using kind of the brute force approach. And we can do the same thing for the short base diode. The short base diode means that the quasi-neutral regions are very short compared to the diffusion lengths. And here is a graph of the excess carrier concentration. The point right here is delta Pn of 0, and it goes to 0 at the contact. This W is the end of the quasi-neutral region. Notice that the slope is constant in this case, therefore the current is constant. Unlike up here, which is really bad because the current goes to 0 before it even gets to the contact. Here the current is constant throughout the quasi-neutral region, and at the contact the charge is just collected, and we have a high current all the way through. In this case, relatively straightforward. The area under the curve, which is the total charge, is just equal to the 1/2 the base times the height, and we put all that in, and we get immediately that the current, which is constant, is given by equation 1253, and the difference here is instead of having LP, we have W, and W is much smaller than LP, so the current is higher and the current is constant. Okay, so now we're going to embark on a long, well, not so much long journey, but a hopefully not too painful journey in finding the diffusion current in a media with arbitrary width and arbitrary recombination times. So we're not going to specify whether it's short base, whether it's long base. It is somewhere in the middle, and we're looking here at the depletion, at the quasi-neutral region for holes, and the holes are going to be minority carriers here. And let's just, before we actually go through the mathematics, look at 4 different cases here. This is the best case, number 2. Number 2 says that the current is constant because the slope of the excess minority carrier concentration is constant. 1 is the worst. 1 means that the slope decreases and we get no current out. 3 is a rather strange case because 3 says that, okay, the current doesn't quite go to 0, but at the contact, it immediately goes to 0, which implies an essentially infinite diffusion, because here we have a fair amount of excess depletion or excess carriers, and all of a sudden they drop to 0. That's not terribly realistic. But the case that we'll be covering is case 4, where we're having arbitrary depletion, arbitrary quasi-neutral region, and an arbitrary recombination time. And here it is. Okay, so we start with the same thing that we started way back when. For the exponential case, we have a decreasing exponential and an increasing exponential. Remember before, we let A2 go to 0 because it wasn't realistic that the current or the excess charge could possibly increase. Here we don't do that. A2 is not 0. We do have, however, 2 boundary conditions. We have a boundary condition at x prime equals 0, and at the edge of the depletion region, we have the boost. Here I'm suppressing the -1, and at the contact, the excess minority carrier concentrations goes to 0. So these are our 2 boundary conditions, and if we put in x equals 0 into our solution, we get that the excess minority carrier concentration at the edge of the depletion region, delta Pn of 0 at 0 is just A1 plus A2. We put in x equals 0, so that we have an expression now for A2 in terms of A1, which we haven't found yet, but we do know what this is. We do know what the delta Pn at 0 is. And at the contact, we put in the contact length, x sub c, minus, plus, and carrying through there, we have that delta Pn of x sub c is equal to A1, which we just carry over here, plus A2, but we know we have an expression for A2, so we just put that in here, and now we collect all the terms with A1, we put them into a one bracket, and we can solve for A1. So that's pretty cool. We can solve for A1, and here it sits. We just take the minus, turn to a plus, and reverse these 2 terms to get equation 2.70. And now we have an expression for the excess carrier concentration at any x prime. That's why we have the 2 exponential terms in terms of A1 and in terms of A2. Okay, we're not done yet, but we're getting pretty darn close. I mean, this isn't all that a revolting expression. We know this term here. We know A1 because we've solved for it. So what we do is we put in A1 into here, and then we have an expression. All we have to do is simplify it. Well, it's not that simple, but at least we can, at least in theory, do that. So here I just repeat this term, 271, and I substitute in for A1. Here it is right here. I just stick this into wherever we see A1. I stick it in here. And now we have a complete expression, equation. This should be 1272, not 272. So wherever you see a 2, it should be a 12. Sorry about that. I'll make that correction. And now what we do is we combine these three terms. 1, 2, 3. We get a common denominator. What's the common? It's just combining fractions. The common denominator is shown in the brackets. It's the same as here. So that's our common denominator. We just put down the first term. We put down the third term. This is the third term here. This term here, and the numerator is this term here. And then this term we have to multiply by that common denominator. And that's basically all we're doing here. So this is the mission right now. Our life's goal is to simplify this equation here. And we can write the denominator as a sinh. I'll go into the definition of the sinh, but whenever we have the difference of two exponentials with no imaginary number I, we write that as the sinh. It's just a definition. And then what we do is we basically combine 1, 2, 3, 4 terms. And we combine them into, well, there's 1, 2, 3, 4. And we combine, or we add the x sub c's and the x primes, x sub c plus x prime, x sub c plus x prime, and minus x sub c and plus x prime. So we see that this term here and this term here cancel out, which is very nice, leaving only two terms, 1, 2, and wow, that's the sinh also. That's the sinh of xc minus x prime. So basically what we've done here is we've taken something which looks pretty darn messy and we've rewritten it into a really nice form. And this is an expression for the excess carrier concentration. This should be an n here, a sub n, and this should be a sub n here. I'll make those corrections as functions of quantities we know. We know the sinh, and we know x sub c, and we know LP. All those things are known, and it's just a function of distance. So knowing that, and here it sits in the, again, should be 1275, we have the complete form, the definition of the sinh, I just right here, and basically that is it, because once we have the excess carrier concentration as a function of position, I can differentiate it to find the current using the definition of the diffusion current, and I get that final equation is equation 1276. The derivative of the sinh is the cosh, and basically there it sits. And the nice thing about this is I can use this general expression to find short base, long base, anything I want, simply by comparing x sub c and LP. And I do that here. Let's stop here. We'll take this up in our next session and skip to the bottom. We're going to be looking at all this stuff in our next session. Beside doing some examples, I'd like to share with you a video clip from the movie, I think it's 2005. It's the finale of the movie called Smile. I'll set the scene. The scene here, or the movie, talks about two just magnificent creatures of God. They were born on the same day, but they share a common humanity, but their external conditions are quite different. Katie was born into a luxurious lifestyle in Malibu, California. She grows up, she's a beautiful blonde girl, and she has lots of boyfriends and lots of money and lots of luxury. Lynn, on the other hand, was abandoned at birth because she has a serious facial disfiguration. She was left to die. She was adopted by a righteous individual and raised as her own. their paths cross 17 years later. And let's look at the finale to the wonderful movie Smile. And we'll see you next time.
没事的，一切都会好的。什么？
我想见 Kitty。
好。She wants you.
Len, you really need to get back into bed. Are you scared? A little. I'm scared too.
Narrow daylight entered my room. Shining hours were brief. Winter is over, summer is near. Are we stronger than we believe?
Blood pressure is stable and pulse is stable.
Walls of reputation
Should be out in about 20 seconds.
among the infamous too.
那我们开始吧。Let's go over
As the
recording.
camera clings to the content, beyond all vanity, into a gaze to shoot you through, is the kindness we'd count upon, here in everyone.
你女儿很好啊，
I step
在
down
口腔手术重置牙齿的时候，她流了很多血。不过在面部的植皮整容方面不会有什么问题。我估计她会长成一个漂亮的女孩的。那现在呢？她现在正处在康复状态。谢谢医生，谢谢，不用谢。现在你呀，应该休息一会儿了。啊，好，休息休息。医生，谢谢你啊。
Oh, no, you don't. Come here. I want to show you something.
is the kindness we count upon, hidden in everyone. I
Take you where she can sleep.
stare in a salt spray air, felt the wind sweeping over my face, ran up through rocks to the old wooden cross. It's a place where I can find some peace.